All right, hi everyone. Hopefully you can hear me okay, and welcome to today's session on heat and temperature. It's a particularly well-timed session, I think. Feel free just to pop a hey in the chat. In general, throughout today, we're going to split the session that we're doing into two parts. So we're going to have two halves, and in each half we'll learn some stuff, and after we've learned some stuff, we'll do some practice exam questions on the stuff we learned. Throughout, not only in the exam questions, but also in other parts of the session, I might just ask questions to see if everyone's understanding, if everyone's along with us. So feel free just to tap answers in the chat if I ask any questions. And if you have any questions while I go through things, just type them in the chat. I'll be keeping a lookout. And assuming I have enough time, etc., I'll do my best to answer any questions you have or anything I've said that I'm confused about. Okay, so hopefully that all sounds good. Like I said, just let me know if you have any questions about anything we're going to be going through. And with that in mind, let's get started. So just by means of a little introduction, I am Matt. So I'm the lead physics teacher here at SatProvise. I'm also a physics PhD student and have been an A-level physics tutor for the last 6 years or so. Okay, so that's enough about me. Now about the lesson. So today our objectives are split into 3 parts. We're going to define the internal energy of a substance. We're going to try and understand the Kelvin temperature scale, and we're going to try and understand absolute zero. Okay, finally, we're going to calculate and describe the changes to a substance when it is heated. Okay, so some things we won't cover today, but we certainly do cover on the StatRevise website, are the ideal gas equation and kinetic theory. Okay, great. So usually before we start a session, before start the 2 main parts of the session, I would like to do a review of some of the stuff that we're going to be referring to throughout the session. So this is going to be some things that these are going to be some things that it's useful to have in the back of your head as we go through the session. Okay, so maybe the first most important thing that's going to come up today is the idea of a melting or a freezing point. Okay, and we'll have the same for boiling and condensing points too. So melting is the process of going from a solid to a liquid. Good. Okay. And then, so that's melting. And then freezing is the opposite. Freezing is the process of going from a liquid to a solid. So one key thing to know is the temperature at which water melts or freezes. Can anyone say in the chat the temperature at which water melts or freezes? So it's melting / freezing point in degrees centigrade is 0 degrees centigrade. That's actually, I expect, why we called it 0 degrees centigrade at some point. Okay, good. So next we have boiling and condensing points. So those are the points at which we have substances which change between liquid and gas. Okay, so boiling is the process of going from liquid to gas, and condensing is the process of going from gas to liquid. Okay, good. And this happens for water at 100 degrees. Okay, good. Now let's talk about kinetic energy. Can anyone put in the chat what the formula is for kinetic energy? Yeah, perfect. It is 1/2 of mv squared. Good. The kinetic energy is 1/2 mv squared. And if we take a look at this formula, it's telling us that we have some mass which is in some way moving. In other words, it has some velocity. The more mass you have, the more movement the mass has, the more kinetic energy you have. In other words, kinetic energy is the energy due to motion. Okay, good. Okay, and then there's potential energy, and potential energy is a kind of a label that you can use to talk about a broad class of kinds of energy that are around. So potential energy is usually referred to as the kind of energy that we have due to the presence of some non-contact force. Okay, so when we say a non-contact force, we're putting under a big umbrella there things like the gravitational force, things like the electric force, things like the magnetic force, etc. Okay. So that's all we probably need to know to get stuck into today's session. So here's the spec points we're going to go through in terms of the three main exam boards. So the three main exam boards we have here are AQA, OCR, and Edexcel. Okay, good. And let's finally get started. So we're going to start by talking about internal energy and temperature. So good. Let's start by defining the internal energy of a substance. The internal energy of a substance U is the sum, we'll explain this definition once we've written it down, the sum of the randomly distributed kinetic and potential energies, kinetic and potential energies of the particles in our system. So of the particles in our substance. Okay, so a substance here we can think of as some collection of particles or molecules. So for instance, here is one example of such a collection. Here is another, and here is another. They all look quite different. They have different properties, but they all represent some kind of a substance. Okay, good. Now, this internal energy is the sum of the kinetic energies of all the particles and the potential energies. So why do these substances have potential energies? Well, each of these particles may be attracted or repelled from each other. For instance, often due to some kind of electric force, due to the electrons these particles have. And what else was there? Ah, yeah, the kinetic energy. So it's often the case that these particles, in fact, always the case, these particles are actually moving at all times. Let's use a different color for that. We have these particles, they're always vibrating. So these two arrows I've drawn around this particle represent the fact that it's kind of moving up and down periodically. So each of these particles has a kinetic energy. That's how fast it's moving. It has a potential energy. That's about how strongly attracted it is to all the other particles. And this is going to be randomly distributed. This is a big, messy system. You can see this more in maybe the latter two cases. Particles are jumbled around in random places. Some are going to be moving faster than others. Some are going to be closer together than others. So that's why the kinetic energies and potential energies are randomly distributed. Okay. So the particles are randomly distributed, but we can talk about the kind of substance they create as a whole. And when we have a very nice arrangement like this into a lattice, we call what we have a solid. This picture we've drawn here is going to be used to represent a liquid. And this picture here is going to be used to represent a gas. Okay, so in these pictures, which of these substances do we think is going to have the highest highest kinetic energy? Yeah, good. You can kind of see it in the picture, right? The gas particles here are moving around. They look as if they're moving faster, and they indeed, in general, will be. So the gas particles have the highest kinetic energy. In terms of the convention we use for potential energy, it turns out that they also have the highest potential energy. This essentially represents the fact that they have done the most bond breaking already. They are the most apart from each other, which actually is something that we assign the highest potential energy to. Okay, good. So liquids, well, let's say solids. Solids have the lowest kinetic energies, and they have the lowest potential energies, which actually means they're the most tightly bound together. And then the liquids are in the middle, of a medium amount of kinetic energy and a medium amount of potential energy. This means that altogether, gases have the highest internal energy. Remember, we use the symbol U for internal energy. And then the solids will have the lowest internal energy. Okay, so you may well know that if you want to turn a solid into a liquid or a liquid into a gas, you need to supply heat or do work on your substance. And so to increase the internal energy of a substance, you need to either supply heat or doing work on the substance. Okay, what does this mean? This means that, for instance, we could take one of these materials and light some kind of a fire underneath it, literally supplying heat to it. This would increase its internal energy. But something else we could do is we could apply a pressure, for instance, and make the solid smaller. We could squeeze our solid. That would essentially be doing work on it, and that would also often increase the internal energy. Okay, so similarly, if we want to decrease the internal energy, we should remove heat or let the system do work. Oh, I said two, I meant do. So for instance, if you just put some ice on the material and extract some of the heat, that will reduce its internal energy. But something else you could do is you could allow the material to expand. And allowing the material to expand would essentially be allowing that material to do work on its surroundings and thereby use up and lose some of its internal energy. Okay, fantastic. So that's the definition of internal energy. Now we're going to move on to the definition of temperature. Okay, so let's imagine we have two objects which are in contact. We say that they are at the same temperature if they are in thermal equilibrium. Now that's just a fancy phrase, so we need to explain what that phrase actually means. Thermal equilibrium. So what is thermal equilibrium? Well, let's imagine in general, we take a situation like we were talking about before. We have some material and we put a block of ice next to it or something. Then in general, we had this idea that heat would flow from one system to the other. Now, if instead we had some even hotter material on the right-hand side, then heat would have flowed in the other direction, from the hotter material to the cold one. Two objects are in thermal equilibrium if the rate of flow from A to B is the same as the rate of flow from material B to material A. And if the rate of flow of heat from one to the other is the same as the other way around, that's a way of saying they have the same temperature. So, okay, that's a nice conceptual way of thinking about temperature. It's like relative heat flow. But we want to start putting numbers to temperature. This is, I'm sure we are aware at the moment, a useful, important thing to be able to do. So let's start by introducing the notion of absolute zero. So absolute zero is like the lowest possible temperature you could ever have. And we're going to call that lowest possible temperature zero, and it will be 0 kelvins, not 0 degrees. Okay, so absolute zero is the temperature when particles have no kinetic energy. Okay. And minimum potential energy. Okay, so you can't always get the potential energy down to 0, but the kinetic energy you could imagine getting to 0. Here's the idea. Remember that the solids were the materials where the particles had the least kinetic energy. That essentially means that the particles weren't moving around very much. The solids were also the coolest, so we could imagine cooling even further. And if we cooled far enough, maybe eventually the particles would just genuinely stop moving altogether. Absolute zero is the temperature at which the particles of your substance would actually stop moving altogether. Okay, good. So the absolute zero scale measures, for temperature, measures, we'll write this sentence down, then we'll explain it, measures linearly from absolute zero up to and actually beyond the triple point for water, in other words, the melting and freezing point for water, the triple point for water at 273.15 kelvins. 273.15 kelvins. Okay, so all you need to take away from this sentence is the point that 0 degrees centigrade is 273.15 kelvins. Those are the same number. Okay. So in general, if you want to find out the number of kelvins that your temperature is, you find your temperature in degrees centigrade, and then you simply add on 273.15 to the number. Okay, good. So we can draw ourselves a graph. So on this graph, we are essentially drawing our energy against temperature, kinetic energy in particular, kinetic energy. Okay. And then the point was that we have 0 kinetic energy at a temperature of minus 273.15 degrees centigrade. And so that's what we call 0 kelvins. As a result, when we get to 0 degrees centigrade, what we're looking at is 273.15 kelvins. Okay, good. Yes, the physics exams, I believe, have concluded for this year, but we just do these all throughout the year. So we do this all throughout the year, so you can think of this as getting a head start for the next year now. Okay, good. So how's everyone feeling about this? Yeah, so the main thing Kelvin is used to do is just to have 0 be the lowest possible temperature. If you use degrees centigrade, there are temperatures below 0. You could have -5, -10, -12. And this is just a bit inconvenient. It's more convenient in a physics perspective just to have the 0 be the lowest possible temperature. Nice. Okay, good. Okay, so let's have a go at a quick exam question, then we'll look at the second half of the session where we have actually a lot more exam questions. Okay, so in this question, we're asked to describe the motion of atoms in a solid at a temperature well below its melting point. So what state of matter is this in, this material? Is it a solid, a liquid, or a gas? If it's well below its melting point. Absolutely right. Below its melting point means it's a lower temperature than the point at which it would melt, so it is still indeed a solid. So the motion of the atoms in solid at temperature well below its melting point. You're absolutely right. Small vibrations. So atoms held together in a lattice and vibrate slowly around their equilibrium points. Their equilibrium positions. Good. Okay, part 2. What is the effect of a small increase in temperature on the motion of these atoms? Okay, cool. What would the increase? What would the effect of an increase in temperature be on the motion? They will have more kinetic and more potential energy. So that is almost true. It turns out, and we're going to talk about this more in the next section, the temperature is actually specifically a measure of the kinetic energy. So all we need to say here is the atoms will gain kinetic energy. Kinetic energy. And so vibrate faster. Good. Okay, just let me know if there's any questions, and we can take a look at the next half. So in this section, we're going to look at heating a substance, and we're going to specifically look at the different kinds of energy transfers that can happen when we're looking at heating up a substance. Okay, so let's start by talking about temperature change and change of state. And this might answer the comment that I was just talking about before in terms of temperature and kinetic energy. So usually when a substance is constantly heated, what do we mean by this? We mean, let's imagine putting some kind of a flame, say from a Bunsen burner, directly under our substance. So that is constantly heating it. We're constantly adding energy to it via heat. When a substance is constantly heated, generally its temperature rises as the atoms gain kinetic energy. Okay, good. So far, so good. So we can see this on the graph. Let's say this is a graph of temperature against time as we leave our Bunsen burner under this substance for some time. And we see the longer we leave it, the more heat that we add, the higher the temperature goes. But then something weird happens. We get to some point where time goes on, so we keep on adding energy, and yet the temperature doesn't increase. So at certain temperatures, the temperature will not rise for a while. So the temperature will not rise. Okay, so this is strange. This is something we need to explain. This is because the energy goes into breaking bonds. Okay, so usually as we add the temperature, what happens is these particles in our material just start to move faster and faster. But at some point, we put in so much energy that rather than just moving faster and faster, these particles actually break away from each other. They stop being bonded. They're no longer in a lattice. They're moving around randomly. And this process of breaking bonds, this doesn't add to the temperature. The temperature is about rate of motion. It adds to the potential energy instead. Breaking bonds. So all through here, what's happening to potential energy? In other words, we're breaking bonds rather than increasing the temperature. Okay, so let's say we had a solid up until this point. What kind of material do you think I have here once the temperature starts to rise again? No problem. Good, absolutely right. Once we've broken all those bonds, we're no longer in any kind of a lattice, and we're now in a liquid. And now we have a liquid, the energy goes into raising the temperature again until we reach a new point. So at this new point here, something happens. We seem to break some bonds. What kind of state of matter will be in by this last X here? Yeah, perfect. By this point, we're going to be a gas. Great. Okay, so we've understood from this slide, and this will be important to remember, there are two kinds of ways that energy going into our system can increase our internal energy. It either goes into our kinetic energy, thereby raising our temperature, or it goes into our potential energy, thereby changing the state of matter that we're in. So this is going to be a key thing going forwards. Two types of energy change. Change of temperature and change of state. Okay, so now let's put some quantification, some numbers into the discussion of change of temperature. I actually can't remember where plasmas are supposed to be on this. I think they are even more hot. Is that correct? So I actually can't remember. I'm not sure. Certainly you don't need to know it for A level. I remember doing it at uni at some point, but it's fallen out of my head. Yeah. Okay. So let's talk about specific heat capacity. Specific heat capacity is a way of measuring how easy it is to change the temperature of some substance. Sometimes I add a bit of energy to substance and its temperature skyrockets. Sometimes I add a bit of energy to a substance and its temperature will barely change. That's a material property that we call the specific heat capacity. How much heat it can take, how much heat it has capacity for. So the specific heat capacity of a substance C is defined to be the heat energy. And then we're going to put some pers in here. Per unit mass. I think there'll be more pers. Per unit mass. No, that's all required to raise the temperature by 1 degree. And it doesn't matter here if I say 1 degree centigrade or I say 1 degree Kelvin. Either is fine. Increasing by 1 centigrade is the same as increasing by 1 Kelvin. It's just that 0 centigrade is not the same as 0 Kelvin. Okay. So let's study this sentence as an equation. Okay, so I'm going to write down the equation here. The change in energy is equal to mc delta theta. Okay, we're going to need to explain this formula. So I'm going to label the quantities and then I'm going to show how it is that this equation represents the same thing as this sentence on the left-hand side. So this delta theta here represents change in temperature. So we sometimes use theta rather than T to represent temperature. This C here is what we called the specific heat capacity. It's the thing we were defining in the previous line. And this here is mass. So let's try and understand this. Let's rearrange for C. If we rearrange this equation for C, we get energy over mass change in temperature. Let's imagine that the change in temperature was 1, as in this definition. Then what this equation says is the specific heat capacity is the heat energy per mass. So divide by mass required to raise the temperature by 1 degree. Okay, so that's the relationship between the two definitions. There's a mathematical definition and a wordy definition, but they say the same thing. Notice that if I have a bigger heat capacity, that means I need more heat energy per mass to increase the temperature. Okay, so higher heat capacity means it's harder to increase the temperature by just adding energy. Okay, let's have a go at an example of using this equation, this new concept. Here, we're going to try and calculate the temperature of 500 grams of water at 23 degrees centigrade after 36 kilojoules of heat is supplied to it. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Okay, so I have this formula that I'm probably going to want to use because they've mentioned specific heat capacity. So I should write down the formula where specific heat capacity is defined. What if they asked us to calculate the temperature? So our goal is probably going to be to find out this thing. So we're going to try and rearrange for it. So the change in temperature is the change in energy over mass times specific heat capacity. This is great because we've been told the energy that went in, 36 kilojoules. So that's 36 times 10 to the 3 joules. Have we been told the mass? Yes, we have 500 grams, although standard units are kilograms. So it should be 500 times 10 to minus 3. Specific heat capacity, we were told this here, 4,200. Okay, good. So you can chuck all of that into a calculator and you should get around 17.14, etc. degrees centigrade. So that's the change in temperature. Initially, we had 23 degrees. So what should I do to find the new temperature? Well, heat was supplied, so presumably our temperature increased. So we started at 23, but now we've added another 17.14, etc., which once you round off to two significant figures is 40 degrees centigrade. Two significant figures. Good. Okay, hopefully that's making sense so far. We're now going to move on to talking about change of state. Specific heat capacity was all about relating energy that you put in to temperature change. But now we're going to talk about the relationship between energy you put in and the amount of mass you've managed to change the state of. Okay, good. So we're going to define specific latent heat. And there's one for what we call fusion and one for vaporization. But either way, it is defined in the following way. The specific latent heat of fusion or vaporization of a substance is the heat energy per mass needed to change the state, i.e., fuse or vaporize. Note that fuse here just means freeze, really. Change the state of the substance. Okay, so this one's actually easier to write down in a formula. Change in energy is equal to mass times L, where L is this latent heat number. So let's label that. L is the latent heat. M here is mass. Change in energy here, so that E represents energy. Again, if we rearrange for L, we see that L is equal to change in energy per mass, which is really what this sentence was saying. It's the heat energy you got to put in per mass. That's what we see here. Heat energy per mass. Good. Okay, so let's have a go at a question. In this question, we are asked to calculate the temperature of 170 grams of water at the point of boiling after 420 kilojoules of heat is supplied to it. The specific heat capacity of water vapor is 2000 joules per kilogram per Kelvin, and the specific latent heat of vaporization is 2.3 megajoules per kilogram. Okay, so something interesting here is this has got to be a slightly more complicated question. Why? Because we've been told the specific heat capacity and we've been told the latent heat. So we're probably going to have to use this formula, change in energy equals mc delta theta at some point. And we're also going to have to use this other formula, change in energy equals ml. Now, these might not necessarily be the same changes in energy. So, okay, with that in mind, let's take a look at this question again. Calculate the temperature of our water at the point of boiling. Okay, so this is really cryptic, but actually quite important. If the examiner tells you something's at the point of boiling, that means if we go back to our graph, we are at this point here. This is the point. This is a liquid at the point of boiling. In other words, not here, not here, not here, right here at the start. So we have a liquid which is at the temperature such that now any energy that goes into it will go into changing state, but none has gone in yet. So it's all at the initial state. All energy that goes in will go into changing state until we get to this point here, and then the energy will go into changing temperature. So the idea is we're going to have to use our formulas twice. The energy equals ml bit will apply here, and the energy equals mc change in temperature will apply here. Okay, so let's go back to our question. We're at the point of boiling. Okay, 1 second. There we go. We have 170 grams of water at the point of boiling. We add so much heat to it. The specific heat capacity of water vapor is so much. The specific latent heat of vaporization is so much. We want to calculate the final temperature. So we're at some... We're initially water. So we're initially at the point of boiling, which is 100 degrees centigrade. We know some energy will have to go in to get us into the gas state. And then the rest of the energy will go into changing our temperature, and we want to find out that final temperature. So let's start off. We know that this is how much energy goes in total. Let's find out how much is needed to do the change of state. The rest will go into changing the temperature, and that will allow us to calculate the final temperature. So, okay, let's calculate how much energy it would take to boil all our water. Well, the energy required to boil all our water would be the mass times the latent heat, which is going to be our 170 grams, but we want it in kilograms, multiplied by the latent heat, which is 2.3 megajoules per kilogram. So that's 2.3 times 10 to the 6 joules per kilogram. Okay, so if you chuck that into a calculator, you should get, and I just need to check something quick. Need to expand something. Good. Yes. Okay. So that should give you 391 times 10 to the power 6 joules. Okay, now notice that we started with 420 kilojoules, in other words, 420 times 10 to the power 6 joules. So we are going to have some energy left over. So what is the energy left for a temperature change? Well, 420 is going to go in all, times 10 to the 6. But we're going to have to use up 391 of that on boiling our water. So altogether, that leaves us with 29 times 10 to the power 6 joules. Okay, good. So this is how much energy goes in here. It's 29 times 10 to the power 6. So now we can calculate the change in temperature. The change in temperature is equal to the change in energy, which is 29 times 10 to the power 6, divided by the mass, which is 170 times 10 to the minus 3 again, divided by the specific heat capacity, which we had here. It's 2000. Okay, so chuck all of that into a calculator. Let's actually calculate the final temperature, which is going to be this plus 100. So we started at 100. Altogether, chuck that into a calculator, and to 3 significant figures, you'll get 115 degrees centigrade to 3 significant figures. In other words, the change in temperature was 15 degrees centigrade. Okay, good. Hopefully that's making sense. Does anyone have any questions? How confident are we feeling? Oh, isn't it 10 to the power 3? Ah, yeah, you're right. You're right. It should have been 10 to the power 3, not 10 to the power 6. That was just a typo from me. Yeah, you're absolutely right. Every times 10 to the power 6 I wrote should have been a times 10 to the power 3. But yeah, other than that, any questions? No. Okay, well, just let me know if you have any questions as we go through. We have some exam questions that we'll do now. Okay. Okay, so this is a really good question, actually. This gets you to really mix up your understanding of heat capacity and latent heat altogether, kind of like the last question did. Okay, molten lead at its melting temperature of 327 degrees centigrade is poured into an iron mold where it solidifies. The temperature of the iron mold rises from 27 degrees to 84 degrees, at which the mold is in thermal equilibrium with the now solid lead. Okay, so the mass of the lead is so much. We're given some pieces of information here. Maybe we should draw a picture of this. Molten lead is poured into an iron mold. Okay, so here is an iron mold. It's just a place where we can pour our molten lead into. Here's our molten lead. Okay, cool. Let's try and understand the situation here. Originally, now let's draw ourselves 2 pictures actually, because there's an initial and a final situation. I think this will help us. So initially we have our lead, which is poured in. Now let's read the question. Initially, the molten lead is at its melting temperature of 327 degrees centigrade. 327 degrees centigrade. Poured into our iron mold where it solidifies. The temperature of the iron mold rises from 27 degrees centigrade all the way to 84 degrees centigrade, at which point the mold is now in thermal equilibrium with the lead. So by this point, the mold is also at 84 degrees centigrade. Okay, good. So we've got this initial and final state. And we're told some useful bits of information: the mass of the lead, specific latent heat of the lead, mass of the ion, specific heat capacity of the ion. In the first question, we're asked to calculate the heat energy absorbed by our iron mold. Okay, so this is the iron, this is the lead. Okay, so how can we calculate the heat energy absorbed by the iron mold here? What formula could we use? We know that the temperature of the iron changed, and we know how much by. So which formula should we use? So we've been told the specific heat capacity, and we've been told its mass, and we've been told the change in temperature. So we know pretty much everything other than the energy in the equation. Change of energy equals mc times change in temperature. So that's the one we want to use. And we know the mass. The mass is 3 kilograms. So specific heat capacity is 440, and the change in temperature is 84 minus 27. Now, notice that I didn't bother to change into kelvins here, and that's because we're dealing with a temperature difference, and the difference in temperature is the same in degrees as it is in Kelvin. Okay, if you chuck all this into a calculator, you will get around 75,240 joules. In other words, to 3 significant figures, 75,200 joules. Okay, good. And that's the 3 significant figures. Fine. Next question. Calculate the heat energy given out by the lead while it is changing state. So we have molten lead at the melting temperature. So what does that mean? If we imagine we draw ourselves that graph again, it's molten, so it's liquid. So it's somewhere along here, and it's at its melting temperature. Well, if I had solid here, it would melt along here. Okay, so it's at this point here. This is our molten lead at melting temperature. Okay, the heat energy while it changes state. Well, the molten lead was initially a lot hotter. It's going to become solid as it gives its energy to the iron mold. So we're looking at the energy released as it gets to this point here. Heat energy given out by the lead while it is changing state. Well, this time it's change of state. So the formula we're going to use is change of energy equals mass times latent heat. Here we have been told the mass again, it was 1.2. And have we been told the specific latent heat of fusion? Yes, we have. It's 2.5 times 10 to the power 4. Okay, good. Chuck all of that into a calculator and you'll get 30,600. So 30,600. And that's in joules. Okay, good. So hopefully that's making sense so far. This question continues. Okay, so in the next part of the question, we are asked to calculate the specific heat capacity of our lead. Okay, so we need to think about what we know here. So let's go back to our picture. We know that the lead must have lost a load of energy to get to this point here. So I lost my pen. Let's also draw in a different color. Let's draw it like this. Okay, so let's draw our graph again. We know that to get to this point here, what happened? Well, we gave away, our lead gave away 30600 joules. And we know that altogether, by the time it got to its final temperature, it had given away in total 75200 joules. So that's going to allow us to figure out how much energy was given away at this point here. And we know the initial and final temperatures. Okay, good. So, because we know the initial temperature is 327 degrees. And we know the final temperature, because they ended up in thermal equilibrium, is 84. So we know the change in temperature. And we're going to be able to figure out how much energy was released. That's going to allow us to calculate the specific heat capacity. Okay, good. So let's just head straight on. We just need to check something here. 1 second. Okay, my apologies. We just need to check something here. Yes, my apologies. So I made a slight typo here. This 30600 was actually 3000. So 3000. Okay, good. So with that in mind, we can have a go at this question now. So we're going to calculate the specific heat capacity of lead. How are we going to do it? Well, let's start by calculating that change in energy as our lead decreases in temperature. So the actual change in energy as the temperature of the lead changed is given by 75200. That's the total energy released minus 30000. And if you chuck that into a calculator, you'll get 45200 joules. Okay, good. Now we can calculate specific heat capacity. Remember, change in energy is mass, specific heat capacity, change in temperature. So specific heat capacity is change in energy over the mass times the change in temperature. Okay, the change in energy is 45200. We need to look at the mass. Well, we're looking at the lead, so the mass is 1.2. They give us that in the table at the top. And we have the change in temperature, which we observed was 327 minus 84. Okay, so chuck all that into a calculator and you'll get 155 joules per kilogram per Kelvin. Good. Okay, so finally, we're asked to state one reason why our answer to part C is only actually an approximation. Okay, so this is a classic kind of question. Why is it that our calculation involving transfers of heat energy is only an approximation? Well, it's almost always because some heat energy is lost to the surroundings, Good. Okay, so we have one more exam question to take a look at. And this one's more of a conceptual one. Okay, good. So we're given a graph, and the graph shows the variation of temperature with time for a fixed mass of a substance when heated by a constant power source. At A, the substance is a solid. At E, the substance is a vapor. Okay, so here's our graph of temperature against time. In part I, we are asked to describe the changes taking place in the kinetic energy and potential energy of the molecules for the following sections. And we start off with A to B. So in A to B, what is increasing? Our kinetic energy or our potential energy? It's one of the two. Can anyone in the chat say which one it is that's increasing here? It's the kind of energy that increases when our temperature increases. Good, absolutely right. So that's the kinetic energy. The Ke increases, Be stays the same. Okay, what about from B to C? Which one is increasing here? The kinetic energy or the potential energy? So in this section, our temperature isn't increasing. So what's happening here is we're breaking bonds. Good, absolutely right. So the potential energy increases and the kinetic energy stays the same. Perfect. Good. Okay, so final part of the question, we're asked to state and explain what we conclude from figure 4.1 about the specific heat capacity of the substance in a solid state in comparison with the specific heat capacity of the substance in the liquid state. Okay, so we're in a solid state here, and we're in a liquid state here. Now let's think about the specific heat capacity. So this is a general principle here. So over some constant interval of time, we're essentially putting in some constant interval of energy. Okay, so we can see that from A to B, when we put in some width of energy here, we get quite a big increase in temperature. Whereas when we put in that same bit of energy here, we get quite a small increase in temperature. Okay, remember, specific heat capacity was about how easy it is to change the temperature. If it's hard to change the temperature, you have a high specific heat capacity. So, like if we look at this formula again, change in energy equals mc delta theta. So C equals energy over mass times change in energy. So, okay, if you need more energy, if you need to put more energy in for the same temperature change, then you have a higher specific heat capacity. Here we have the same temperature change in both cases, but in C to D, sorry, we have to put in a lot more energy, so we have a higher specific heat capacity. So there is a higher specific heat capacity at liquid state as seen by the shallower gradient. Good. Okay, so hopefully that is making sense. Does anyone have any questions about this? So in fact, I may as well put us onto a questions page. So you should now be able to define the internal energy of a substance. You should be able to understand the Kelvin temperature scale and absolute zero. And you should be able to calculate and describe changes to a substance when it is heated. And so now indeed, do you have any questions? So I'll look out in the chat for any questions that you have. While I'm looking out for any of those questions, I do have just a short thing to mention about some of the other stuff that we do as Snap Revise. So web classes on YouTube are one of the many things that we do. Actually, we have courses on our website, but also each year we do what we call our seminar series. Okay, so let me see. Can we say the gradient of the line is inversely proportional to the specific heat capacity? Yes, you absolutely could say that. You're absolutely right. In fact, that is exactly true. Yeah. Okay, so some of the other things we're doing at SAPRevise, something we did a couple of months ago was the A-level exam crash course seminar. So this is something that, of course, happened before, but you can still purchase, if you like, the recording of these sessions. Okay, so these should be really handy for exams. The idea is you could use them to get 100% exam ready. And we, in particular, during these sessions, we studied exam technique, trickier topics, and we had our own revision booklet called the seminar booklet that we gave out, which you would also get as part of purchasing the recording. So I'm just going to explain a bit about what each of these things was. So in terms of exam technique, this is kind of an interesting one. So rather than just going through the various bits of the syllabus that we think are the hardest, although we did do that, we spent like a whole hour or so at the start just talking about how to extract information from exam questions. And we gave a kind of system for doing this, a systematic way to do this. So we talked about how to break down questions into what we call command words. We covered the whole range of kinds of questions that you could come across, from the 1 markers to the 6 markers, from the states to the explains to the plan and experiment style questions. And we gave some step-by-step approaches to make sure you're earning all the marks when you are answering each of those kinds of questions. We then looked at doing some of the trickier topics. Sorry, 1 second. So we revised some concepts from what we figured were the most challenging areas of the course. And we used the exam technique skills that we learned at the start. We put them into practice throughout the rest of the session. Okay, good. So if you are interested in that, then you can get yours now here by clicking this link. And I'll just check the chat to see if there's any more questions. Okay, so I can't see anything else on there. And actually, with SnapRevise, I'm about to go and do another web class on the SnapRevise website. So I will shoot off and go and do that now. Thanks so much for listening, everyone. And I hope this was useful, and catch you at the next one. Okay, bye.